Hey, how's it guys? Welcome back to my channel. In less than 24 hours, a significant partial lunar eclipse will occur in our skies. Weather permitting, I will be out there filming it as it unfolds. But before the event begins, I want us to walk through the exact mechanics of what is about to happen. Long before modern streaming or internet debates existed, orbital mechanics already established a predictive framework that allows us to map these celestial alignments with absolute mathematical precision. We aren't guessing what the sky will do, we are tracking a physical system on a clockwork schedule. To understand an eclipse, we start with what we physically observe from the ground. Depending on how the alignment lines up, we see three distinct visual outcomes. A penumbral eclipse occurs when the moon glides through only the faint outermost fringe of Earth's shadow. It causes a subtle dimming, almost like a soft tea stain across one side of the lunar surface that most casual observers often miss entirely. A partial eclipse, which is what we will look forward to tomorrow morning, happens when a section of the moon crosses into the deep central core of Earth's shadow, creating a sharp, unmistakable curved boundary across the lunar disk. And a total eclipse occurs when the entire moon enters that central shadow completely, taking on a deep coppery red tone. The reason we get these distinct visual phases is that any solid object illuminated by a light source casts a two-part nested shadow into space, the penumbra and the umbra. The penumbra is the outer region where Earth blocks only a fraction of the sun's direct light. When the moon passes through this zone, sunlight is merely reduced, creating that light shading. The umbra is the solid inner cone where Earth completely blocks out direct sunlight. The moment any part of the moon intersects with the inner shadow, we observe that distinct dark curved boundary. A physical external body is blocking the light source. There is no other mechanism in nature that can produce that specific geometric boundary. Even when the moon is submerged inside that deep umbral core, it doesn't vanish from visibility into complete pitch blackness. This comes down to Earth's atmosphere acting as a lens. As sunlight passes through the blanket of air surrounding our planet, shorter wavelengths of light, like blues and violets, are scattered away in all directions. The longer red wavelengths, however, bend through the atmosphere and project inward into the shadow cone. The reddish glow seen on the shadowed portion of an eclipsed moon is literally the collective light of every single sunrise and sunset taking place around the perimeter of Earth at that very second. Because orbital paths are fixed and measurable, astronomers categorize the progression of an eclipse using five specific milestone markers known as contact points. P1, first penumbral contact. The exact minute the moon enters the outer shadow, visually subtle, but mathematically the start of the event. U1, first umbral contact. The moment the moon touches the dark inner core, this is when that clean, dark bite first becomes visible. Maximum eclipse, the peak of the alignment where the largest portion of the moon is submerged. U4, final umbral exit. The moon completely leaves the dark inner shadow. And finally, P4, final penumbral exit. The moon fully clears the outer shadow, ending the event. Applying these exact coordinate calculations to my location tomorrow morning gives us a clear roadmap. At 3:23 a.m., P1 begins high in the western sky. By 4:33 a.m., we reach U1. The dark umbral bight will begin creeping across the lunar surface. Maximum eclipse hits at 6:12 a.m., where over 93% of the moon will be submerged deep within the dark umbra, revealing that warm coppery hue across the shadowed region. Notice that for my location, the schedule ends right around maximum because the moon will set at approximately 6:33 a.m. South African Standard Time, just as dawn is breaking. The second half of the event, U4 and P4, will take place after moonset below my western horizon. Weather permitting, we might capture a setting eclipse in the morning twilight, making a clear western view absolutely essential. We know this predictive model is accurate because real world observations confirm it every single time. Predictive science does not rely on beliefs, opinions, or speculation. It presents a model, gives you the exact time and coordinates, and invites you to look up and verify it with your own eyes. The geometry is set, the maths is already done, and now we just wait on the weather. If the clouds do clear for tomorrow morning, I'll have fresh observational data to compare against these predictions. I hope you come back for the actual observation. In the meantime, thank you so much for watching. Please, guys, stay safe, and I will catch you in the next video. Wish me luck. Bye.